Welcome, everybody. Thank you for being here. This is the first CLaME sponsored lecture. I'll say, so what is that? Many of you know, many of you perhaps don't. It's a newly established center that's a collaboration between NYU and the Max Planck Society. It just opened in the spring. Today is our first lecture. So what is CLaME? It's a Center for Language, Music, and Emotion. If you're more European, you can say CLaME for giving an extra emphasis. So it's run from the NYU side by Kate here, and Joe Ledoux, not here, and me here. And on the German side by colleagues there. Why these topics? Because language and music and emotion are endlessly fascinating and endlessly deserving of more study and experience, and of course are sort of they're the experiences that are quintessentially human. And those are things we enjoy among other things the most. Also, incidentally, they're the things that AI is pretty bad at. So it's remarkable that the things that we're good at, damn those AI guys, they're bad at it. But so it seemed fitting and very fun to have as the first speaker in the series, or a speaker that I'll introduce in a second, in case you're already planning ahead. So what are we going to do? We're obviously going to do research on these topics, and we invite you to join us in various forms. We're going to have workshops, symposia, lectures, and all kinds of things. Actually, the next event is already scheduled, and that will be October 15th, which is Philippe Schlenker, who's sitting right there, taking a peek at how it works. The event after that will be in Frankfurt, which you are also invited to, November 4th and 5th, which is a workshop on emotion. Get there yourself, though, which is, I think, sort of co-organized by Kate and Joe Ledoux and others, which is really focused on emotion. So those are, and if you have any questions about this, and if you want to buy in or buy out or confused, please ask Kate. Don't ask me. So today's speaker is wonderful. Psyche is wonderful. Thank you for agreeing to be here to be our first speaker in the series. We very much appreciate it. The cool thing about Psyche is a professor at Northeastern, where she has an amazing title. She's also a professor at Wesleyan still. But the amazing thing are her titles, her job titles. So at Northeastern, she's a professor of creativity and creative practice, which is kind of awesome. And at Wesleyan, she has many titles, but is a professor of integrated sciences, which is also awesome, which basically allows you to do whatever you want. I always thought, my very first job, I thought I had a really cool job title. I was a professor of linguistics and zoology. And I thought that was pretty weird, but I think yours are way better, or way cooler titles. So, if you work at all on music, perception, cognition, and music related, you will have come across Psyche's work in perception and production, on neural correlates, music processing, on work with patients, and so, in many different areas, some of which we'll hear about today. Correct me if I'm wrong, I think Psyche got her undergraduate degree in psychology and neuroscience from Duke, then was a PhD student at Berkeley, you see Berkeley, working with Wessel and Irv Hafter, very distinguished psychophysics people, then worked at Harvard, so a lot of weird institutions, Duke, Berkeley, Harvard, with Gottfried Schlauch, and has then been a professor at multiple places, which seems to be the thing of the future. Always be a professor at multiple places.
High five.
Go. And so Psyche sent a wonderfully poignant, complicated, seductive title, Learning, Liking, and Learning to Like. Statistical learning as a guiding principle of musical creativity and emotion. Thank you for accepting the invitation. We look forward to hearing from you. Thank you for allowing me to play your music. Congratulations, and we look forward to your talk. Thank you.
Thank you for that kind and amusing introduction, David, and thank you for inviting me. It's such an honor to be here, the inaugural lecture of CLaME. So today I'm going to talk about a few lines of work that are relatively new, but some are relatively old, and some are old, but I'm circling back to think of them in new ways, which is kind of nice when you get to that point in life when you can think about your old stuff and learn some new things from it. We're talking about CLaME or CLaME. So it's one of those once-in-a-lifetime privileges when you get to start your own lab. You get to name your lab. My lab is called the MIND lab, where MIND stands for Music, Imaging, and Neural Dynamics. And in the MIND lab, I spend most of my time thinking about why we have music, right? And what can music do for us. And so the fundamental question is, how is it that sounds, which are sound vibrations of air molecules on your ears, how do we translate that into something as complex and beautiful and individually varied as the musical experience? Can you guys hear me in the back, by the way? Okay, great. Okay. And in the past couple of years, I've spent quite a lot of time thinking about a specific kind of music ability in music making, which is musical improvisation. And I think that's particularly interesting because it's a bit more like how we do how we go about our everyday lives, right? So when we're going around talking, having conversations with people, we're not doing overlearned sequence making, right? It's not an overlearned sequence production task, it's a real-time creative task, right? So we're making lots of minor and small but important decisions about what counts and what should go in the next spot, which is something that musicians do in their in musical improvisation all the time. And in thinking about what musical improvisation entails, I was very inspired by David Marr's seminal work on vision. Well, if vision is a complex system, I thought musical improvisation is definitely a complex system. Marr talks about a few different levels of a complex system, right? So at the top level, you have a computational level, right, which is the goal of the computation, right? So for vision, it's to see, but for musical improvisation, it is to take some kind of semantic reference. Let's say autumn leaves, right? So a lot of jazz musicians, you say autumn leaves, and you'll have that melody in your head. So that's a semantic reference that you then filter through your knowledge base, right? So your licks and your melodic riffs, your rhythmic grooves and so on. And then you turn that knowledge into patterns, auditory motor patterns, that you then execute, which hopefully you find rewarding. Right, so that's the goal of musical improvisation at the top level. And then at the next level, we have an algorithmic representation, right, which is about the process, right, that performs this input-output transformation. And I think that from reading a lot of work on improvisation and also on creativity more generally, I think of musical improvisation as a combination of generative and evaluative processes. It's a bit like the process of blind variation and selective retention, where you start out with generating a lot of possible ideas, and then you evaluate those ideas and you retain the ones that are good. Right? So it's this generative and evaluative cycle. And then at the bottom level, of course, we have the implementation, which is the hardware and how that enables the representation. And so, of course, we have the brain. From the work that had been done up to when we started to think about musical improvisation, most of the story about where in the brain improvisation happens. Of course, there's not one single area, but it does tend to be distributed among a few areas within the frontal lobe. Right? So some of them are more lateral areas of the frontal lobe, some of them are more mesial areas of the frontal lobe. So in embarking on this project on musical creativity and improvisation, we wanted to compare a few different groups of musicians. Right? So in our study, we compared non-musician people with no particular musical training, right, but who nonetheless have been exposed to music in their lives, against classically trained musicians, so mostly people from the school orchestra, and then compared those against jazz-trained improvising musicians. Right? So the idea being that jazz improvisation generally entails improvisation, training in generating new instances of auditory patterns, whereas classical musical training, you still make those auditory motor patterns, but you're not choosing how to improvise, you're not choosing what note to play on a note-by-note basis. Right? So 3 groups, and we had people come into our lab. Our lab is sort of like that, not exactly. I think that the new lab is going to have more of these colorful lights. But people come in, sometimes they bring their instruments, we have a piano for them to play, they do free play, play whatever they want. They also do some structured playing tasks that I'll talk about. It turns out that structured playing is a much better tool for examining how musical improvisation works than just free play whatever you want. Then we also have psychophysical and psychometric tests, and I'll describe those in a moment. We also do EEG, and we also have a few different kinds of MRI. We have diffusion tensor imaging to look at white matter structure of the brain, and then we have resting state functional connectivity MRI to look at functional connectivity. All right, so how do we quantify something as elusive as musical improvisation? So here we have a very simple task that is, we call this the improvisation continuation task. And it's really to evaluate musical improvisation, right? So we start out by playing these simple motifs, something like this. Yeah, come on. It's always something. Maybe just let me exit out of... Did I... Now, can you, if I go and play that again, can you still see it? Okay, so that's one of 12 different motifs I would play. Then we also have this other one. All right, and so these musicians come into the lab, they listen to the motifs, and then they get to play it back, right, so copy it, and then they have to riff off of it. Right? And so here is one example of a person with no particular musical training. It doesn't sound so particularly inspiring, but they're generating something. Now let's compare that against a jazz-trained musician. And the amazing thing is every time you ask them to do it, it's a different riff, right? I can copy that, I can't quite play it. I can't quite make a new thing every time. So how do you quantify these sorts of performances? So we started with pretty simple recordings, MIDI recordings and audio recordings, and we just thought, well, we'll just count the number of notes, right? So you might have noticed that the more experienced player made more notes, so that's a measure of fluency. Then you can also look at the information content within the performances. So entropy, Shannon entropy, it's just a measure of how much information content there is. And not surprisingly, you can hear it, but jazz musicians played with more fluency and with higher entropy. Right, so does this actually correlate with anything that an expert might consider to be creative? Right? So we paid a couple of expert musicians who were jazz instructors. Ferrone is more of a free jazz guy. John Baboyan is more of a classic jazz guy, and got them to rate all these performances for creativity, and they were quite highly correlated, and their ratings of creativity were highly correlated with both entropy and fluency. Right, so far I've shown you that jazz musicians can indeed improvise, which shouldn't be so surprising, but we also wanted to take things out of just the musical domain and look for a more domain general measure of creativity. Right, so to that end, we turn to divergent thinking task, which is a pretty generally used, commonly used neuropsych assessment for creativity. So one example item is list all the uses you can think of for a paperclip. So I won't try this on you guys. So, at first somebody will say, put paper together. That's 1 point for fluency, 0 points for originality, because everybody else is going to have said the same thing. But sometimes you hear something like, oh, use paperclip to transfer squirrel poop. And so maybe nobody else said that. That's a pretty high originality statement, right? So we score each person for fluency, which is the number of items they produce, and originality, which is the inverse of the number of people who also produce the same response. And we compared again jazz-trained musicians, classical trained musicians, and non-musicians, and it turns out that while both classical and jazz musicians scored higher than the non-musicians on fluency, the jazz musicians scored higher than the non-musicians in originality. Right? So suggesting that there's something about jazz training that can be translated outside of the practice room and can translate to more creative ability outside of music. So where might this come from? Right? So this is kind of a top-level characterization of what creativity looks like in jazz-trained musicians. But I wanted to get to a more mid-level cognitive understanding of how these jazz musicians might be implementing their real-time creativity. And I think one thing that's quite an interesting idea is that maybe having more of a knowledge base as a jazz-trained musician might help you translate your auditory motor patterns to form more possible predictions. And so maybe the predictions is what we should actually be looking at. So in music cognition, we have quite nice tried and true methods for probing musical expectation or musical predictions. You can use these lovely chord progressions. So I'll just play you them. All right, so that's like saying I take my coffee with cream and sugar. That's like saying I take my coffee with cream and NutraSweet. Right? So there's a Neapolitan chord in the middle, which is slightly unexpected, but it's still grammatical. Right, so nobody would write that, and so unless you're a music cognition researcher. And so that's like saying I take my coffee with cream and socks. Right? So it's ungrammatical. So of course, highly expected, slightly unexpected, very unexpected. And people just had to listen to these chord progressions and rate how much they liked the chord progression on a scale of 1 to 4 while their EEG was being recorded. So we're getting some real-time as well as some offline measurements of how individual groups process musical predictions. So here's what the behavioral results look like. So first of all, the non-musicians and the classically trained musicians all preferred the highly expected, cream and sugar. They all disliked the cream and socks. And then curiously, there's a group by expectancy interaction where the jazz group actually preferred the slightly unexpected. Right? So they thought that the cream and NutraSweet was actually better than the cream and sugar. And so so it seems like there's something about increased preference for unexpected that characterizes these jazz musicians. So then looking into how the brain is processing these chord progressions, here I'm showing you in the black line the event-related potentials in response to the highly expected chord progression, right? So the sugar. Right? And in red, I'm showing you the event-related potentials in response to the unexpected, so the socks. And so at around 200 milliseconds after the onset of that chord, the jazz musicians are already showing a right lateralized negative waveform. So this is the early right anterior negativity, which has been shown since year 2000 by Statistical and colleagues to be a marker of musical expectation. And then around 400 milliseconds, everybody's showing some sensitivity to expectation. Right? So, and this is shown as the frontally centered P3A waveform, as well as the parietally centered P3B waveform. But everybody shows a P3A waveform, whereas only the first two groups, the jazz-trained musicians and the classical trained musicians, show the P3B waveform, whereas the non-musicians don't seem to show much of a P3B. And then, around 800 milliseconds after the onset of the unexpected chord, I actually think this is the most fascinating. The jazz musicians are actually back to baseline. They don't care anymore. They've heard it, they've forgotten it. The classical musicians are still ruminating about it. They're actually showing this late parietal positivity that is unique to the classical musicians, whereas the other two groups don't show it. Right, so just summarizing the same results, but now looking at difference waves, comparing high and low expectations. Again, jazz musicians, I'm showing jazz in blue because the jazz musicians play the blues. The jazz-trained musicians are showing the early right anterior negativity, so showing earlier sensitivity to unexpectedness. Everybody shows the middle sensitivity, whereas the classical musicians are still showing late sensitivity. So I think to me, this really gets at what it means to be a jazz musician, to be an improviser. Right? So in order to improvise, right, to be generating a lot of stuff in real time, you have to be sensitive to expectancy. And that sensitivity has to be registered quite early on. So you have to be sensitive in a very time-sensitive manner. But then you also have to accept unexpected events as being part of your repertoire. Right? So I think this late positive waveform, and that is really highlighting that difference between classical musicians and jazz musicians. I myself am a classical musician. Right? When I hear something slightly unexpected, I feel like that's wrong, and that's out of tune. Whereas a jazz musician, I mean, I've worked with some jazz professors now through this project. They accept everything as being possible, plausible alternatives of their environment. So I think that really gets at the difference between classical training and jazz training.
Can I ask something about the subjects? Does it matter what instrument you play? That's to say, so suppose you take jazz musicians that play the upright bass versus the violin, where probably the modulation rate on average of the instrument is very different. So you might have much longer scale expectations. So is there an interaction between the instrument and expectation?
So we had a couple of bass players in our group. They didn't show anything like very different from the other jazz players. But I think the point is well taken. That depending on whether you're a rhythm section kind of person or a melody kind of person, you might have different forms of expectation. Yeah. So the short answer is not so far, but we don't have enough power to be so far. And so in case you don't believe me that these event-related potentials have anything to do with creativity, we also measured divergent thinking test performance on all of these participants, and we saw that the early right anterior negativity and the P3B waveform are correlated with fluency and originality, right? So suggesting that which means that the more fluent you are of a player, the larger of an E-rank you show. So moving on from time-sensitive measures to more whole-brain functional connectivity measures, we also looked at the resting state functional connectivity using resting state fMRI in these three groups. And for this particular project, we were interested in a couple of networks. And this is based on work from that I've briefly mentioned earlier from Beatty and colleagues that had suggested that there are a couple of frontally centered networks that are probably useful in creativity, and that includes the default mode network and the executive control network. And so we seeded these two networks, and we looked for differences in functional connectivity between the groups. So right now I'm showing you the seeded areas that are correlated with the executive control network. And so again, in blue I have the jazz musicians, in red I have the classical, and the minimally trained non-musicians are in green. So you can see that even though we're seeding a lateralized frontal lobe network and the executive control network, we see a lot of functional connectivity to the midline regions, including areas that would be typically thought of as the default mode network. And especially we see that in the improv group, right? So there's some overlap between the different groups, but most of that is driven by the improv group. And then furthermore, this functional connectivity was correlated with divergent thinking task performance and the improvisation task performance. And in other words, the better you tend to do in these two tasks, the more functional connectivity you have from those seed regions. So that was pretty exciting. And then we also did the same with the precuneus network, so which is part of the default mode. And again, we see more functional connectivity from the precuneus to midline regions that are mostly the default mode network, especially in the jazz trained musicians. We also looked at the structural connectivity in addition to functional connectivity using diffusion tensor imaging. So now this is just a whole brain comparison of white matter connectivity using the track-based spatial statistics TBSS approach. And so in green are the areas, voxels of the brain that are part of white matter. And in red are areas that are specifically showing higher fractional anisotropy, right, which is a measure of white matter integrity. Jazz musicians actually have higher FA in the regions that I'm showing in red. So that includes the cingulate and also in the corpus callosum. And so we thought, well, isn't that interesting, right? So that means that the jazz musicians who are more creative have more left and right hemisphere structural connectivity. And so what does that mean, right? Does that mean that areas in the midline of the brain are just talking more to other areas on the lateral parts of the brain, right? So we took the red regions as the seed region of interest, and we said, find me connections to other areas of the brain. Right? So, and those other areas of the brain we seeded in the inferior frontal gyrus and the superior temporal gyrus, which we know to be important for auditory perception and action. And what we saw was that the jazz musicians, sure enough, had higher fractional anisotropy between the midline regions and these endpoints of the auditory motor network. Right? So suggesting that it's not just that this area is more talking to itself, or that it is that the midline structures are more connected to the lateral structures in the jazz musicians. So I think, I'm kind of going through this quite quickly because I want to get through to other parts of my talk. But so far, what we've learned is that these perception and action areas that are important in the superior temporal gyrus and inferior frontal gyrus, they are quite important for implementing these generation and evaluation, which is part of the algorithm that enables musical improvisation. I think that what jazz musicians are trying to do, as part of their improv training, is to generate, take lots of perceptual reference, right, and generate from this lots of possible actions. However, what the classical musicians might be trained to do is not necessarily generate lots of possible actions, but evaluate their own actions. Right? So if you play a note that's out of tune, you have to evaluate the outcome of that action perceptually. So I think there's more of an emphasis on evaluation in classically trained musicians. And so the underlying networks that seem to enable this, I think we're able to say with a little bit better granularity that this involves the auditory motor network, and then the default mode, and also executive control networks. So, any questions about this so far?
The one thing I'm a little puzzled by is, maybe it's my misunderstanding of the default mode network, but aren't you super active when you're improvising? I mean, you're doing actions, you're listening, you're evaluating. I thought that's associated with the down-regulation of the default mode network, not an up-regulation.
Right, so the party line so far has been that if you're doing nothing, then you activate the default mode network. But I think this is not showing that the jazz musicians are doing more of nothing. It is that the default mode network is more functionally connected with lateral networks, so there's more of a flipping back and forth that the jazz musicians are kind of doing at rest. Yeah.
Can you see them? I mean, can you see the networks coming in and out of activity? Sort of a counter phase activation pattern or something?
Yeah, so I can show you that later in one of the later slides.
Okay.
If you have,
So the two differences between the jazz musicians and the classical musicians, one is the corpus that they're used to, the other one is whether they improvise. The other one is whether they improvise. So do you have data on classical musicians who improvise, or data on people who listen to a lot of jazz music, or even play some jazz music, but without actually improvising? So in other words, do you find these more minimal effects of improvisation as opposed to corpus?
Yeah, that's a really great question. We haven't really looked at expert listeners yet, although, I mean, this is kind of the first step in comparing different kinds of musical training. I mean, it's surprising that the music cognition field has mainly focused on classical training up to now. So this is, I feel like it's biggest effort towards moving away from that. But of course, you can then ask lots of questions about, are you an expert listener versus an expert player, or a part-time player as opposed to a full-time player. I think that the main difference is that in order to qualify as an improviser, you have to be generating actions. Right? So if you're one who always generates actions from perceptual reference, then you would show the same patterns that I'm seeing in the references. Matt?
Do you have a sense of the tracks that you showed that were different in the DTI study of what kind of predefined what meta tracks those are?
Yeah, so this is part of the cingulum, and then this is part of the corpus callosum.
Next one, or those,
Yeah, so these, I think they're still part of the corpus callosum, but then they're moving on towards, they probably involve a lot of the U fibers that are kind of kissing the other major pathways, but I think it's going to be a combination of superior longitudinal vesiculus and the corpus callosum. Yeah. All right, so I wanted to get from this into why this, why brains have evolved to have music in the first place, right? I mean, going back to my question about musical knowledge, right? We're able to take sounds and infer from it a musical experience. People around the world make music. It seems to be a very fundamentally human ability. And we can take a few different routes to understanding where the source of that musical knowledge comes from. Right? You can go across different parts of the world and find people who make different forms of music and compare music like across around the world, like Pat Savage and colleagues have done. You can take babies from the first day of life and try to probe their brains and try to understand what it is about music that they know or don't know. So something like Hank and Honing has done. You can even go across different species and look at what other species might know about music, such as this is the famous Snowball. And some of you have heard of Snowball. He's like the Backstreet Boys of music composition work. So he's been for more than 10 years now been shown to have lots of dance moves and also very creative dance moves, it turns out. So this is something that Untitled has done. Or you can look at the vast general population. And I think that's particularly insightful because most of us know music without specifically being taught to do so. Right? So much of our musical knowledge is implicitly acquired. So really to get at that source of the implicit knowledge that we all have, I think it's helpful to actually think of your lab as a new world, a new environment. And then bring people into your new musical environment and see how they learn. All right, so I'm talking about completely reinventing music here. It's just tiny goal. Take music that is different from all existing sources, and then watch people as they develop knowledge in that system. All right, so how do we do that? All right, so first of all, what do we know about the regular musical system? So musical systems around the world are based on the octave, which is a 2-to-1 frequency ratio. And so the Western equal-tempered chromatic scale is based on 12 logarithmically even divisions of that octave. Right? So this is a lovely Western chromatic scale. Now in contrast, the Bolin-Pierce scale, right? John Bolin, Heinz Bolin and John Pierce independently asked, why does it have to be based on 2? Why can't it be based on 3? Right? And so then they worked out the math and they said, okay, let's. It turns out that you can have a 3-to-1 frequency ratio, which is twice it instead of an octave, and you can divide that into 13 logarithmically even divisions of that 3-to-1 frequency ratio. So it sounds like this. And so why 13, right, you might ask? So it turns out that, and this is what Bolin and Pierce both figured out, it turns out that if you pick certain notes along that scale and you play them together, they approximate whole integer ratios in frequency. And we've known since Pythagoras that these whole integer ratios in frequency sound good together, they sound consonant together. Right? So that's what the word symphony means, is that they make sympathetic vibrations because they are whole integer ratios related to each other. So we take these notes, right, each of which falls along n to form a note within the volunteer scale. So we're at 0, 6, and 10. So that together forms a good chord, a new chord. Again, so this is the frequency that can be determined by the n. And then you can string a few more chords together, and now you have a chord progression. And so this is the beginning of the grammar. Right? So you can have one original chord progression, and then you can also play a trick that Schoenberg and composers in the 20th century have made, which is make a retrograde version of that same grammatical system. Right? You can take a chord progression and you can play it forward and play it backwards. And so the nice thing about that is now you have two parallel existing worlds, in which each note happens the same number of times, but the transitional probabilities, right, the probability that one thing follows the previous one, is different. And so this is what a chord progression sounds like. All right, so that's the retrograde chord progression. All right, so now we have a chord progression, and from there we want to generate lots and lots of melodies. Right? So we can apply a finite state grammar set of rules. Right? So each of these notes can serve as a node in your finite state grammar, and it can either repeat itself or it can go forward to the next chord. Right? And then you can apply this with for all the possible nodes in your finite state grammar. And so you have many, many possible paths through the grammar. So this is one of many possible melodies. Okay, so this is now a new musical system that is systematic, that is quantifiable, that is testable. So the first question is, can we actually learn this new musical system? All right, so we have a very simple design. People come into our lab. They do a pretest where we assess what they know before they hear any of the BP melodies. Then they listen to the melodies for half an hour, and then they get post-test where we assess what they've learned, and then we compare the pre and the post. And the basic questions we started to ask is, first of all, can you remember something that you just heard? Right, so I play you a melody, and then I play you again. Can you tell that the melody sounds familiar? And so this we assessed using a two alternative forced choice test of recognition. Right, so at test, people were given pairs of melodies, one after another, and one of them belongs to the set of set of melodies within the grammar that they've heard, and the other one doesn't. Right? So, and then people were asked which one sounds more familiar. Of course, if you choose the one that's grammatical and that you've heard it before, then it means you've remembered something. But then I'm also interested in a more sophisticated form of learning, not just memory, but can you learn new melodies, right? So if I played you something, and then I play you something that's from the same grammar, can you say, okay, that sounds more familiar, right? So this is a two alternative first choice test of generalization, where you get two melodies, one after another, neither of which you've heard before, but one is grammatical, the other is not. Right? So if you say that the one that's grammatical is more familiar, then that suggests you've learned something about the grammar. All right, so this is now, I'm plotting the results as a function of set size. So over the course of many, many experiments, we exposed people to different numbers of melodies. And so for recognition, there was a control experiment where people didn't hear any melodies, and so of course they didn't learn any melodies above chance, so that's good. If they heard 5 melodies over and over again for 30 minutes, they were very, very much at ceiling as being able to recognize those as being more familiar. And then as we increase the number of melodies, we get a drop-off in recognition. But people, even after they've heard 400 melodies, one time each over the course of 30 minutes, they were still able to say above chance that sounded familiar, which is quite remarkable. Then in contrast, we looked at generalization performance. Again, if people don't hear anything, they don't learn anything, which is good. But if they heard 5 melodies over and over again, right, so we're talking about 100 repetitions of 5 melodies, they actually don't pick out new instances of the same grammar as being more familiar to them. But then as we increase the number of melodies, they actually start to be able to generalize. So there's something about the variation of melodies within the grammar that you were given that then gives rise to generalization as in learning new instances of an underlying grammar. So I think that's a pretty exciting overall result. But of course, this is kind of for people who are really geeky about learning new music. But most people don't listen to music because they want to learn it. Most people listen to music because they like it. Right? So we ask, can you actually learn to like new melodies? Right? So at test, again, people had their half hour of exposure to these new melodies, and then we played them melodies that were either familiar or unfamiliar. Right? So in the grammar that
Sorry.
did they get hung up on? And then then people actually just make preference ratings for just rate how much they liked the melodies. And now I'm showing you on the y-axis the difference in ratings between familiar melodies and unfamiliar melodies. And again, you can see that when there are 0 melodies, people don't particularly like the melodies that they have heard because they're not familiar. But as you repeat, the more number of times you repeat a melody, the more they actually become preferred. So I think putting that together, right, I'm interested in preference, I'm also interested in learning, but there seems to be a double dissociation between generalization, as in learning the new grammar, and preference change, as in loving what you heard. Right? In that the preference change is the pattern of results for preference change is more like the recognition results than it is like the generalization results. So I think the implication there is that there are many formal predictions, all of which are everything I've been doing so far is about forming predictions for musical sounds. But depending on the conditions of these predictions, you can have more varied predictions and you can have more repeated predictions. Variation gives you learning of grammatical knowledge and the underlying structure of the sounds, whereas repetition gives you familiarity, and this familiarity seems to drive preference change and possibly reward. So I think that's quite an interesting implication so far. I'm looking to test that more, of course, in future work. But I also wanted to dig a little bit deeper into sort of the cognitive aspects of it. What is it that we learn from the Bowen-Pierce scale? Right? So are you actually learning to expect more frequent tones? Are you learning to expect transitional probabilities? Right? So as I said, because of the design of these experiments, the number of tones, times each tone occurs is the same between the two grammars, but the transitional probabilities are different. So what I've shown so far is that people can generalize, which means that they are learning transitional probabilities. But can you also pick at the event frequencies of individual notes? And so it turns out that music cognition research has had lots of ways to look into this. So the most notable way is using probe tone ratings tests, where people get a melody and then a tone, and you have to rate how well that tone fits the preceding melody. And it turns out if the melody is in C major, then you rate C as being most highly fitting and most expected, and G as being the most expected, and so on. So these probe tone profiles, right, that you can get from the probe tone experiments match the frequencies of compositions, and they're kind of a window into what we know about the statistics of music. So can we do this with the Bowen-Pierce scale? All right, so this is, I'll give you guys this trial as a pre-exposure trial. Oops. Alright, so you heard a melody and then a tone, and you're supposed to rate how well that last tone fits the preceding melody on the scale of 1 to 7. And ratings? 11, 2. Okay, answer's 2. Okay. So this is the pre-exposure ratings, right? And this is the exposure. This is the profile of exposure. So each person is going to hear like tone 0 1,000 times and so on. And the pre-exposure ratings, you see that there's some correlation between the two lines, but not a whole lot. And then after exposure, this is the post-exposure ratings. You can see that there's much higher correlation between the two lines. Now, if you just plot the correlation between the blue line and the red line, you can see that there's an increase in correlation after exposure, right? Suggesting that there's that you learn something from the statistical structure of the melodies over during exposure. Now, some people might ask, right, why is it that there's so much pre-exposure correlation? Does that mean that people are already coming into the experiment knowing something about the scale? So what's up with that? It turns out that in order to obtain these ratings, you have to give people one instance of a melody. Right? So this is what they heard again. Right. And so we have to hear that melody once and then make a rating. So you can partial out the influence of the melody from the ratings, right, from the influence of the exposure set. And when you do that, the partial correlation shows that the pre-exposure correlation drops to 0, really suggesting that you didn't really know anything about the musical system before you came in, but you were rapidly taking advantage of everything the experiment offered you to build a new structure in your head. All right, so that's very exciting. I find that very, very satisfying. People really don't know anything. They come in, they get exposure to a new musical system, and then they learn stuff, and then they leave. Right? So we've taught them something. But of course, everything I've shown you so far is just is pure tones, right? Which is not very musical. Real sounds, of course, are made of mixtures of frequencies. So I'll play you 2 tones, and I want you to tell me what's different about them. So, same pitch, what's different about them? All right, does anyone know what those 2 instruments are? Yes. Who's that? Was that Mary?
Yeah.
Okay, great. All right, so the first one was a flute and the second was a piano. They're playing the same note, same fundamental frequency, A440. Right. Just looking at the spectrogram of these different instruments, you can already see that given the same fundamental frequency, the pan flute has a lot more sparsely distributed frequencies. So you can take a slice of that sound, right, and now I'm going to rotate this sound so that the long frequency is now on the x-axis, and I'm showing amplitude on the y-axis, and you can see that fundamental frequency of the flute note is right at 440. Now I'm going to overlay the pan flute on top of that, and you can see how, unlike the flute, right, which has the next overtone is twice the fundamental frequency, and then the next one is 3 times. So there's the whole integer ratios that are related to the fundamental frequency. The pan flute, in contrast, the next most important overtone is actually 3 times the fundamental frequency, and the next one is 5 times, and the next one is 7 times. So the odd harmonics are stronger in the pan flute timbre. This is because it's a closed tube and so on. So there are physical properties of the instrument that constrain the timbre that it produces. Now, 3 to 5 to 7 should sound a bit familiar to you, given what I've already said, right? So Boland and Pierce both realized that that 3 to 5 to 7 chords that are 3 to 5 to 7 ratios together can make very good chords, and therefore the Boland-Pierce scale is based on 3 to 5 to 7 ratios. So if we really think that there's something about these ratios that give you a cue towards your musical system, you should expect that a pan flute is a better instrument for playing Boland-Pierce music. So that's kind of what we, and you should expect that playing Boland-Pierce scale music in the pan flute or pan flute-like timbres should help you learn the Boland-Pierce scale better. So we're kind of pushing at the constraints of the statistical learning system here. So then the question becomes, do simultaneously presented frequencies, as in timbres, help you learn sequentially presented frequencies, as in melodies? If so, then hearing the tritive, or Boland-Pierce, in tritive-based timbres should help you learn the tritive. So we made a few versions of kind of well-controlled Boland-Pierce melodies. So again, the pure tones sound like this. And then we made shepherd tones, which are artificially generated tones that have a stable overall spectral envelope, but have components, overtone components that are spaced apart in whole integer ratios. And we have generated two versions of timbres, some of which are 3-to-1 frequency ratio apart, whereas others are 2-to-1 frequency ratio apart. Right? So these are octave shepherd tones, which for those of you who are familiar with shepherd tones, they are normal shepherd tones. And then we made these odd alien tritive shepherd tones that are different. So this is what that sounds like. Let me turn it down. Right? And this is what the octave one sounds like. And again, you have to rate how much that last note fit the preceding melody. And so now I'm just plotting the correlation between ratings and the exposure. And so higher means you've learned more about the correlation. And so these are the results for the tritive shepherd tone condition. These are the results for the octave based shepherd tone condition. So clearly we're seeing an advantage in the tritive timbre. And then if you compare that against the pure tone measurements that I've shown before, the pure tone is really neutral. It's really right in between. So I think that's really exciting because it tells you that something about sound spectrum might dictate your knowledge in music, right? So maybe there's something about the spectrum of odd integer instruments like the pan flute might give you a cue towards what you should know about the musical structure of the Bohlen-Pierre scale, which means that maybe there's something about existing Western musical instruments, such as the Western flute, that might be giving you a cue towards what the Western musical structure should be like. Right? So and then importantly, I think learning from the structure of sound is an ongoing process, and that even as soon as we get into the lab, we're using the information we get and forming from it quite a flexible knowledge base of the new musical system. And so I think a logical extension of that might be there's something about the sounds of speech that, such as from your mother's voice, that you might be using to build from that your language, your linguistic knowledge and experience. How much time do I have? I feel like I have lots of things.
10 more minutes.
Okay. So I think I'll just skip through a little bit of stuff. I wanted to talk a little bit about how we can build from these novel experiences into something that's kind of emotional and meaningful, right? So I've talked a lot about the different systems that might be at play. I think that statistical learning is really a guiding principle that we use to take perceptual information and form from it a knowledge base, right? And from that knowledge base, we can form specific predictions that then direct our musical actions. And hopefully, we find those actions to be rewarding. So then I'm going to move on to talk about the rewarding part of the talk, which is about individual aesthetic responses to music, but I think it could be about art more generally. So I think a lot of you might have had the experience of hearing a piece of music that you love, and then just getting chills, right? Being so sort of physiologically taken over that you can't ignore what just happened, through your ears, right? So the whole physiological mechanism of getting chills is quite interesting, but it's also quite varied, right? So if you survey people for the kinds of strong physiological experiences that they report when they're confronted with really great art, right? Music ranks highly among those stimuli, but also people talk about walking into a really beautiful space and just feeling in awe, right? Feeling in touch with God, or hearing the sounds of poetry and thinking, and feeling like your heart just skipped a beat, right? So this is a kind of smorgasbord of all the major aesthetic responses that people report feeling, right? Some people say that their hair is standing on end, that they're feeling a lump in your throat, right? There's also considerable individual differences in how we experience and whether we experience these chills, right? So most people given a very emotional situation, like seeing your boyfriend come back to life, and your dead boyfriend come back to life, and shows, I don't know, this might be getting a bit old, will show a strong emotional response. But then there are some people who are very, very cognitively, high cognitive ability, but they're just not emotional. And you might think it's just a guy versus girl thing, but then there are guys who cry too. So this is work that's by Matt Sachs, who's over there. He doesn't quite look like that. This is him as an undergrad. So we started to ask, what is it that characterizes the individual differences between people who get chills all the time when they listen to music versus people who don't get chills when they listen to music, right? So we designed this aesthetic responses to music questionnaire, which is based on work by Paul Sylvia. And from that questionnaire, we identified the people who get chills all the time when they listen to music. Right? So this is a chill group. Right? And then 10 controls that are matched for gender. So women are a little bit more likely to report getting these chills. Older people are more likely to report getting chills. Of course, musically trained people are more likely to report getting chills. And then people who are open to experience are more likely to report getting chills. So those are all known in the literature. So controlling for all those different factors, we identified the best 10 non-chill people. Right. So then those people came in, they brought in their favorite pieces of music, and we used one person's favorite piece of music as another person's control. Right? So, and we had them make continuous behavioral ratings for when they were getting chills and how much pleasure they were experiencing when they were listening to the music, while getting their heart rate recorded and the skin conductance recorded. And then, importantly, we compared the different, the brain structure of these two groups using diffusion tensor imaging. So just in case you were curious, these are the most chill-inducing songs that were reported by nice New England college undergrads at the time, 2014 or so. Yeah. Right, so a good smorgasbord of classical music, some pop music, and some, I guess, country. Johnny Cash is my least favorite among those, but sometimes I've heard people say just looking at that list makes me get chills. All right, so here's one typical person's responses, right, in our chills group. Right at the top, we're showing the audio that they heard, right, and then we're showing the skin conductance in the second row, and they're making these continuous ratings for how much pleasure they were experiencing during that music, and then they were also pressing a button whenever they got a chill. And you can see how whenever they reported getting a chill, we tend to have more of these peaks in skin conductance. And so this is summarized here. Right? You get, for the chill group, when they're listening to their favorite pieces of music, you get increases in skin conductance. We also get an increase in heart rate, right? So a decreased interbeat interval in the chill group when they're listening to their favorite pieces of music. All right, so how do we characterize the aesthetic responses to music? Right? So I talked about how we surveyed people for all these different types of strong emotional responses that they experience. So in our aesthetic responses to music questionnaire, we have people rate how often they got chills, how often their hair stand on end. And using that information, you could do a multidimensional scaling, which then lets you make a two-dimensional solution, two-dimensional space of strong emotional responses to music. And I really love looking at this because you can see how everything that pertains to part of the body, right? The heart skipping a beat, heart racing, hair standing on end, pit in the stomach, lump in throat, everything that actually mentions a part of the body shows up on one side of this multidimensional scaling plot. Whereas everything that's more abstract, or Matt calls it transcendental, might be things that are more absorbed, or feelings of awe, or feeling detached, or feeling like you're somewhere else, or recent sense of time. Those show up on another side of the plot. So whereas chills shows up in the middle. Right, so what this means is, among the people who say that they're getting chills, there are some who are more visceral responders, and then there are others who are more abstract responders. So I think that's really fun. Another thing that's really fun is you can also ask how much they like different musical genres, because that always comes up, right? When people say that, when I tell people that I study music cognition, they're always like, oh, what's the effect of genre? And so we also had people rate how much they like rap, how much they like punk, how much they like funk, how much they like pop and jazz and so on. And this is the multidimensional scale solution that we get. You can basically look at this and form some strong predictions, right? If you run into someone who's like on the dance floor and they say, I love reggae, and you can say, oh, you probably also like funk and punk, right? And there's all the Bible Belt genres are kind of here, all the kind of beat-heavy genres are here. So I think it's quite fun to think about all the possible genres as a space. And of course, we're interested in comparing the brain structure as measured by diffusion tensor imaging across the different groups. We're specifically interested in tracks that are between regions that are important for auditory perception, including superior temporal gyrus, and regions that are important for social functions and emotional functions. And here that includes the insula and the medial prefrontal cortex. And here I'm showing you the tracks that we identified in the chill group in the red and the no chill group in the blue. And you can see how there's much larger volumes that we are able to identify in the chill group, right? So suggesting that there are actual structural differences between people who are likely to get chills versus people who are unlikely to get chills when they listen to music. So I think that's a really kind of scintillating result, but in a way it's really not that surprising. If you think about the implications, the social implications of this finding, in a way, like, why do we listen to music, right? It's doing something that language doesn't do. And that's something I think is actually very, I think that pop music and pop artists are very good at finding what that thing is and really talking about it. So this is James Corden talking about it.
There's nothing quite like the feeling when you're listening to a song written by someone you don't know, who you've never met, who somehow manages to describe exactly how you felt at a particular moment in your life. This next artist is able to do that time after time. It's for that reason that she's currently #1 in an astonishing 17 countries. If you've ever had a broken heart, you're about to remember it now. Here performing someone like you, it's the beautiful Adele.
And sure enough, Adele is like #2 on our hit list. Right? So there's something about good songwriting that is an auditory channel into our social and emotional functions. And I think that's what's so special about music. So after that, so when Matt's paper came out, it was very nice that Wesleyan wrote up a little newsletter, blog post about it. And then BW got in touch with me, having read this newsletter. So you guys, when you get published, you should actually contact your newsletter sort of writing people, because that will take you your next paper. It was a really fortuitous opportunity where BW got in touch with me saying, my wife's a Wesleyan alum, and that's why I heard about you, and I have musical anhedonia. I've never understood why people find music to be pleasurable. I don't find it pleasurable. But don't feel bad for me, because I'm an avid photographer, and I enjoy visual art. I just don't understand why people enjoy music. So I thought that was quite curious, and at first I was like, really? And I sent all the tests, all my batteries that I could send, and he scored high, quite normal, higher than normal even, on Montreal Battery for evaluation of the music. He's definitely not a music. He's scored high on all the IQ measures, but he really scored quite low on the reward-sensitive types of measures. And so we've interviewed him at length, and he says things like, well, I see people bopping to music to their headphones in the checkout line at a grocery store, and I just wonder, why would you want to do that? And I feel like that's really quite sad. So he really self-identifies as having a socially debilitating lack of reward responses to music, and he says that he likened it to a coming out experience, if you can imagine that. And he says that he's always grown up around people who are musical, but he's never understood why. And so and he just grew up that way. And then when he after being grown up, he would join these art appreciation groups where he would go to art galleries with his friends, and then his friends would also talk about the Wagnerian opera that they just heard, and he would just not be able to participate in that conversation. So we threw all these neuropsych tests at him. The first one is the Barcelona Music Reward Questionnaire. It's 25 items. You say how strongly you feel the reward responses. BW scored 5 standard deviations below the mean on all of the subscales. And then we also checked that he isn't just generally anhedonic, using the physical anhedonia scale. So things that are non-sound items, so things like, I enjoy good food, I enjoy long walks on the beach, I enjoy a good massage, right? All of these things that are non-musical or non-auditory, he scored normal on. But anything that's auditory, right? I enjoy the rustling of leaves and trees. No, I didn't enjoy rustling of leaves and trees. Didn't enjoy the cackling of fire. Of course, also doesn't enjoy anything musical like organ sounds. Like that. So it's really quite a unique case. And we saw that he really did have less structural connectivity, less volume in structural connectivity that we could identify between the superior temporal gyrus and the nucleus accumbens, which is of course the seat of the reward system. So I think that's just one case, and we're looking for more cases now. But I think that this is a paper that just got accepted today with Amy Belfi, who is of course a graduate of David's lab. We're really trying to sort out the different areas that are involved just by looking at case studies so far and the few published neuroimaging studies. I think the main take-home is that the auditory system and the reward system are functionally and structurally coupled, and that's centered around the superior temporal gyrus and the striatum, with the anterior insula being part of both. And I think this also allows us to make some specific predictions. I think that because the auditory system involves so many more areas than just the superior temporal gyrus, it might be that you can have selective deficits that disrupt auditory predictions, but don't disrupt your reward that you get from music. So I think adding to that, the reward system, to our overall brain networks that are important for motivating statistical learning and music. So I think that now that we've learned a little bit more, I think about the brain systems that are important for enabling the statistical learning, which I think is at the heart of why we know and love music. I think that the future work, is going to be not just about looking at sounds and then how they get translated into the musical experience. Although we have learned that music, it has to involve fundamentally auditory motor sequences with learnable frequencies and probabilities that engage the reward system. And that might actually help us actually back translate and think about what music might be useful in various cognitive functions such as executive control. So I think I will just stop there, and I have lots of other projects I'm quite happy to talk about throughout the course of the day, but I'll thank lots and lots of great collaborators and students in my lab, and we have some funding from the Grant Foundation as well as from the NIH and from the Imagination Institute in SF. So thank you, and I'm quite happy to take up questions.
Psyche. We have a couple of minutes time for questions if anyone has issues right now. Yeah.
So that scale, what was it, the
Olympic scale.
PV, yeah, the PV scale, does that go into quarter tones then, like in the Western scale? Like notes between notes?
No, they don't really go in, they don't align well with quarter tones. They align well with, they don't align with any of the Western intervals, but they're generally a little bit larger step sizes than the semitone.
So how does something perform that music? Like what was that played on a computer?
Yeah, so pure tones you can make on a computer. There's actually been a lovely set of musical performances that were commissioned at Northeastern University. So I'm looking to use some of those stimuli in newer studies. But a few years ago, there was a volunteer scale symposium where they actually constructed new instruments that were spaced further apart than traditional instruments. So the volunteers.
Was this voluntary or punishment?
It was voluntary. There is quite a large culture, and they're interested in these things. Just gotta tap into the right geeks.
Yeah, so it's just like a completely different language that like it's crazy.
Crazy but cool.
Yeah.
And
Yeah, thank you so much for this talk. I find it super interesting. You alluded a little bit to the fact that basically if we switch out a couple of words on your final slide, right, we're not only talking about music anymore, we're really talking about a broad range of important human behaviors and things. So my question is what do you think makes music special though, and might separate it more from example visual arts, which is kind of what I'm way more.
I think that's a great question. I think that I'm more and more believing that what makes music special is that it brings us closer to other people. Does that make it different from visual art? Maybe not. But I think that there's something very unique and interesting about the ability to form predictions, and for those predictions to then engage the reward system. And I think that because music is a temporal art, it unfolds over time, and so our predictions then also unfold over time in quite a natural way. So I think that's what's special about it. I mean, I guess when you're asking about special, then you have to say like special relative to what, right? So there's a bunch of things that make it special relative to language, and I think there's a bunch of things that make it special relative to visual art. And I think it's the temporal aspect that makes it special relative to visual art, whereas maybe it's the reward system and the prediction that makes it special relative to language.
I mean, is vision actually that different in terms of the time domain?
I don't know, maybe we should ask the vision experts.
Because you do make eye movements. I mean, you have to sample the visual world. I mean, you don't have just a static image projected onto the retina. I mean, you sort of sample visual images and encode it in sequences of a different form. So it would be surprising if it were completely different in kind. So appreciating a painting is also looking around and sampling and trying to assemble the pieces into sort of a coherent person that you then like or appreciate or elicit some memories. I wonder if the visual system is also, I mean, we study it, we study the connection to reward systems and other systems in the auditory system. Do we know actually about the visual system? Its connectivity nerds. What's the verdict? Do we know?
So, like, why is it that like hordes of people go to raves and wait for the beat to drop? Like in vision, you don't.
So the social aspect.
There's a social aspect, but I think there's also an expectation aspect that has to unfold. That's like you can't get it until you get it, right? Whereas in visual art, like a painting, you can gradually appreciate it, but you are given it in upfront. Right?
Mm-hmm.
Yeah.
Yes, wait, Ellie.
So I saw that people identified like excerpts of the pieces that gave them chills, like specific sections. Did you look at any sort of commonalities in like chord progression or across genres?
Yeah, I didn't specifically, but John Sloboda has done this in 89 and 91, a couple of really nice papers where the main finding is that people who get chills for music, the chills are usually correlated with changes in chord progression, whereas tears is like the next most common report. That's usually correlated with melodic structural devices, so appoggiatura, so like kind of non-chord notes that are downbeat. So melodic structures are more correlated with tears, whereas chord structures are more correlated with chills. So I think that's a really nice study.
Yes.
Yes.
So, as far as I know, intones also have some sensitivity to what's consonant and dissonant, right, and words. And you are also saying that we can learn to like something and everything. I mean, I
to a certain point. I noticed that I didn't just play random Olympia scale notes to people and expect that they like it. I first generated a grammar, right? So, and the grammar is consonant. So I think that it's going to be very hard for people to learn to like something that's just different. And so I think that's like kind of low, kind of a bare minimum requirement, and there might be something very biological fundamental about that, but we'll see. I think that's still an ongoing debate.
Thank you, Psyche. You've earned lunch. You all have lunch as well, and we appreciate your coming.